Newton was eventually excused from becoming a minister, but he wrote more about theology and alchemy than science and math combined. Only recently made available to the public at the National Library in Jerusalem, these documents are now revealing that for Newton, religion and science were inseparable, two parts of the same lifelong quest to understand the universe.
Newton himself wanted to design a universe in which God was absolutely present and absolutely powerful. There's an enormous irony there. In the 18th century, gangs of interpreters, most of them French, will take the God out of Newton's world. It's a very common image of what the Newtonian world was, that it was soulless, that it was mechanical, that it really wasn't theologically motivated at all.
Now, ironically, that's very anti-Newtonian, because Newton argued that God had to be present. You couldn't read him out of the universe.
The most beautiful system of the sun, planets and comets could only proceed from the counsel and dominion of an intelligent and powerful being.
Newton owned more than 30 Bibles, and he examined them as rigorously as he did the natural world. Correlating biblical passages with astronomical information, he redated ancient history, drawing up elaborate charts and chronologies that show civilization starting around 980 BC.
I have hundreds and hundreds of pages of computations and workings and reworkings where he tries to probe this over a period of close to 30 years. Time and time again, he'll come back to it, calculating and recalculating, trying to make it work just the way he tried to make his theories of light work.
With the same fervor that he brought to science and math, Newton also combed the Bible for keys to the future.
What he was trying to do is determine when the end would come, when Christ would return, when all the apocalyptic events of the end times would come to a head.
And that date is now alarmingly close. The year 2060.
Newton is not a man who keeps his theology in a box that he brings out only on Sundays, and then a man who does his science as a working man the rest of the week. Newton sees his work as a seamless unity, and his project is to understand the truth of God.
Most people today think of religion and science as completely different spheres. In Newton's day, science, the investigation of the natural world, was a part of religion. It was all questions in some ways ended in divine knowledge.
Alchemy and religion might have continued to dominate Newton's thoughts. But in his early 40s, he received a surprise visit that would refocus him on physics. It was the astronomer Edmund Halley, now known for the comet named after him. He asked Newton an esoteric-sounding question about planetary orbits.
My question is this. What kind of curve would be described by the planets, supposing the force of the attraction toward the sun to be reciprocal to the square of the distance from it?
An ellipse.
An ellipse? How do you know?
I've done the calculation.
You have? How did you calculate it?
I'll show you. Should be here somewhere. Don't worry, I will redo the calculations. I'll send you a copy.
Halley's question would change science forever. Through years of observation, scientists had discovered that the planets move around the sun not in perfect circles, but in slightly elongated elliptical orbits. But no one could explain why. Halley and many other scientists had begun to suspect that the planets were attracted to the sun by some kind of force. They guessed that this attraction became weaker with distance in a mathematical relationship called the inverse square law. For example, the inverse square law says that if a planet is twice as far from the sun, the gravitational attraction it feels is 4 times weaker. But no one had been able to prove this resulted in elliptical orbits. Several months later, Halley received a paper from Newton. It was Newton's mathematical proof that a planet obeying the inverse square law of gravity must travel in an elliptical orbit. Newton may have used calculus to arrive at this, but he had not published this new form of math, and his proof was written in the traditional language of Euclidean geometry. But Newton wanted more than a mathematical proof. He wanted to know how the planets moved through space. For the next 18 months, Newton worked on this question day and night. He barely ate, he barely slept, and he saw no one.
When you look at what he did during that time, it's difficult to believe that any one human being carried out this amount of novel mathematical and mathematical physics research.
Finally, he submitted a 500-page draft of his masterpiece, the Principia Mathematica, to the Royal Society for publication.
It is the greatest book of science ever written, bar none. It is the most magnificent work. It is the most all-encompassing work. It is the most daring book of any scientific treatise ever written.
After the publication of the Principia, Newton is the man. I mean, you know, very few people can understand what this thing is about, but a lot of people can see there's something important in here.
What people saw was that Newton was providing a new framework for understanding the universe, building on centuries of work by his predecessors. Galileo had spent years studying motion on Earth and determined that projectiles always follow a curved path, called a parabola. But Galileo believed that motion of celestial objects, like the moon, was very different.
Galileo still believed that there were differences between the terrestrial and the celestial. He retained the idea that was ancient, that motion was different up at the moon and above.
Newton disagreed. He thought the same laws must govern motion on Earth and in the heavens. To demonstrate this, he would have to devise a set of laws so powerful they could explain motion everywhere. He began the Principia with a set of ground rules, his famous 3 laws of motion.
1.
An object in motion will remain in motion forever, unless acted on by an external force. An object's rate of acceleration is proportional to the force exerted on it. And for every action, there is an equal and opposite reaction. These laws allow scientists to make such accurate predictions about how objects move that they are still used today, to send rockets into space and explore other worlds. But explaining the orbits of the planets required another ingredient. This brought Newton back to the work he had begun 20 years earlier on gravity. To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth, and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity.